You can start. Well, thank you, everybody, for deciding to attend this session in the afternoon. I'm Bob Binshadler. Actually, the person who first had the idea of this session is Marco Tedesco down here. He'll be speaking later. And he twisted my arm to join him in chairing, and also Anders Lieberman, who's also a co-chair of this session. The topic is Cryospheric Contribution to Sea Level Rise, Current Estimates and Projections. And this is the oral session. There's some posters as well that I'm sure you're aware of. So without further ado, I will introduce the first speaker. We each have 12 minutes to speak, so we do need to keep well to time. So the first speaker will be Andy Shepard, and talking on a reconciled estimate of ice sheet mass balance. Andy.
Thank you, Bob. You can set my 12 minutes. Right, this is going to be quick. Thank you. This is a paper that was published last week in Science. It was out on Friday, and so it's something that we've been working on for about a year. And so I'll rattle through the first half of the slides and try and concentrate on the results towards the end and explain what we think they mean. So the paper is a reconciled estimate of ice sheet mass balance. There are 47 authors, in case you haven't read it, and it's 7 pages long. And they're from 26 different labs, and most of the people that have been involved in estimating ice sheet mass balance are associated with this paper. It wouldn't have been possible if people hadn't participated actively in the exercise, and it's thanks to everyone's willing cooperation that we've managed to get a positive result out of it. So if you had been at the talk that I gave earlier on today, I talked about what was the initial objective, and that was to try and explain or understand why there were apparent differences in ice sheet mass balance estimates as published from various techniques. As a consequence of the fact that we could explain those differences, we went on to produce this reconciled ice sheet mass balance. And so I'll talk about ice sheets and climates in about 1 minute, the value of satellite data in about 1 minute, and then the reconciled estimate of ice loss afterwards. I don't need to tell you this. We're interested in ice sheet mass balance because the ice sheets could cause a considerable sea level rise. There's no realistic prospect that that will happen in the near future, but the sea level projections of IPCC last time round projected something between 40 and 60 centimeters of sea level rise for the next century. Those were in the absence of estimates of ice dynamical changes, which are well identified in the satellite observations that have been collected over the past 20 years. And in the absence of reliable model projections, we have to use the satellite observations to give us an idea of how the sea level is changing. And so the majority of the sea level rise is through thermal expansion and glaciers, and a minority from Antarctica and Greenland. And there are various processes that lead to dynamical imbalance, and you all know about these, and people have discussed them at length in other sessions. But it's clear that these things are ongoing, and so until we have models that can incorporate them and make reliable forecasts, we use the satellite observations. So there are 3 techniques. Altimetry measures changes in the volume of the ice. INSAR measures changes in the speed of the ice, and we balance that with surface mass balance to get the mass budget. And gravimetry weighs the ice sheet and the rock and the water and the atmosphere and everything else that's around it. So none of them are perfect, but all of them are fantastic. And we're trying to use the strengths of the different techniques and play down their weaknesses. This is the background as why we were doing this. These are past estimates of ice sheet mass balance for Greenland, for example. And so we've got 4 different techniques, altimetry 2, and INSAR and gravimetry. So we have the first estimate of mass balance produced showing that the sea level rise between 1992 and 2000 for Greenland was a very small amount. And then we had another one, and another, and another, and another. And we have, I believe, now 41 estimates of ice sheet mass balance for Greenland, which is a fantastic achievement for all of those people involved. And we all understand why there are differences, but most of the people just want to know what the answer is, and so that's what we try to do. And that's at 1 millimeter of sea level rise. So the past estimates, 30 or so previous publications with about 60 or 70 different estimates in among them since 1989. Poor agreement apparent between the 3 different techniques, and they allow for a combined range of sea level rise that could give you a 0.2 millimeter year fall in sea level or 1.9 millimeter year rise. So we set up this project, the ice sheet mass balance into comparison exercise. It's a community assessment, we believe, supported by ESA and NASA, 47 participants, 26 labs, 10 satellites, 54 years of data. And this is where people live across planet Earth, so it's an international effort. And this is how you do it. So first of all, you find your happy scientific experts. And so we have some here who are experts in ice sheet altimetry, and some here who are experts in ice discharge calculations, and some here who are experts in gravity, and some here who are experts in surface mass balance modeling, some people who are experts in GIA, and some people who are experts in being independent. And most of those people are very happy. There are one or two people who are faking it, and there are one or two people who are looking rather serious. David Vaughan, in particular, needs to smile some more, but he's not here. So the second thing you do is you agree common regions, and this was a rather challenging exercise, but we managed to do it in the end. So this is what Greenland looks like, and this is what Antarctica looks like. We have 3 different ice sheets in Antarctica where we delimited. East Antarctica, the West Antarctica, and the peninsula. Once we've established that, you just have to agree on common time periods, and so we have a bunch of different satellite data which spread between 1992 and 2011. The altimetry and the surface mass balance and INSAR data are the longest. The GRACE data are the shortest. Well, the ISAT data are the shortest, and the GRACE data are somewhere in between. And again, these are all fantastic techniques, but they're operating at different time periods, so we need to assemble them into some single estimate. So we have an overlap period where we intercompare the estimates of ice sheet mass balance over common spatial and temporal domains, and then we have different periods where we assess the mass balance for periods of interest to certain people. So that's AR4, that's AR5, 1990s, and the 2000s. So the first thing we found was that patterns of imbalance between the 3 different techniques agreed, so they all look the same. From INSAR, well, actually, this is the surface mass balance anomaly over a given time period. That's the altimetry, and that's the GRACE. The difference is the dynamical imbalance in West Antarctica isn't resolved in the surface mass balance, but it's certainly seen in the INSAR discharge terms. The second thing is that the estimates of mass balance agree. You might have seen this earlier. So we have 4 different ice sheet regions, 4 different techniques. So for Greenland, they all agree within the uncertainty measurement. This is between 2003 and 2008. For Antarctic Peninsula, they do the same. For East Antarctica, they do the same. For West Antarctica, they do the same. So they're all measuring the same thing when you use the same maps and time periods. So instead of these 41 estimates, we now have 1 estimate of Greenland ice sheet mass balance, which is this single curve, and everybody is really happy about that. And we have a similar one for Antarctica. This is the Antarctic mass imbalance of the full record. East Antarctica has shown a slight growth over the recent years, or if you interpret it in a different way, a negative anomaly of this time period. This is an open question, but most people believe that there's been an increase in snow accumulation over the next few years, which will correct itself. The current uncertainty on that measurement is quite large. The Antarctic Peninsula has been increasingly losing more mass over time, and West Antarctica, as most people know, has been increasingly losing mass over time as well. So we get this final result, which is rather nice, and this is our sea level curves from the whole project. And we have a sea level curve for Greenland, which is the integration over time, and Antarctica as well. So Antarctica has lost 3.7 millimeters, or contributed 3.7 millimeters to sea level since 1992. Greenland has contributed 7.4 millimeters since 1992, and altogether the 2 ice sheets have contributed 11.1 millimeters since 1992, and so that's our single estimate. There are uncertainties on that as well. Interestingly, if you look at the early part of the record, the 1990s, you see that the sea level contribution was about 0.3 millimeters per year, which is at that time about 10% of the global sea level trend. In the last 5 years, at least, the sea level contribution has been about 1 millimeter per year, so it's tripled in total. Most of that is driven by the acceleration of Greenland, but there's a slight increase in Antarctica losses as well overall, notwithstanding the regional variations that I've talked about. Now, that represents about a third of the global sea level trend, and so the ice sheet contribution to sea level is on the up as a consequence of these results. So, well ahead of time. I've got 4 minutes left. I'm going to slow down a little bit. But I've got 3 summary slides. The conclusions are that the techniques actually do concur and are complementary. This is great news for the space agencies because they need to decide which techniques we need to use. And in fact, the answer is all of them are great, and you should fly all of them at the same time, and you should talk to other space agencies to make sure that that doesn't cost as much as it could do. It's great news to people who just want to see the sea level contribution from the ice sheets and don't want to know about our business as well. So it ends this apparent 20-year uncertainty, which is really just mainly as a consequence of the short-term variations in ice sheet mass. And if you cast your mind back to that integrated assessment, there were periods, and I'll go back to it since I can, there are periods when Greenland is losing a substantial amount of ice, and then there are periods where it's not. And it matters very, very much what time period you make the observation. And so a recommendation, or at least an important conclusion from this study, is that short assessments of ice sheet mass balance should be treated with care. The result, as a matter of fact, is about a factor 2 or 3 more reliable or certain than the AR4 assessment. That's obvious because we've got twice as much data that they had in terms of time, and actually more instruments as well in the near record. And so this is a great achievement. We're able to then definitively say things about the ice sheets that we weren't able to do 5 or 10 years ago. And so as a consequence of this exercise, Antarctica has been losing mass throughout the whole record. The second summary are the numbers: 11 plus minus 4 millimeters of sea level rise since 92, as I said, 20% of the global sea level trend, but that's on average over the full time period. 2/3 of that is from Greenland, and Greenland's now losing 5 times as much as it is in the 1990s. People are interested to know these things. The final conclusion is that we hope that this provides a single climate data record that people will use. The data is already freely available on the internet site, so you can go to the website and download that, and people have done that already. And we may do this again at some stage in the future. So I'm out of time. Thank you very much.
Are there any questions?
With a long-term record, how do you weight the different signals that are going into the total signal?
We just take a linear average of the 3 different techniques. There was some discussion that we had 4 different techniques because radar and laser altimetry have some dependencies, but the other techniques do as well. So many of the techniques rely on the same glacial isostatic adjustment models. Many of the techniques rely on the same surface mass balance data sets to provide a certain correction or something like that. But we decided to average the altimeter data sets themselves first to provide a single altimeter result, and then take a straight linear average of the 3 results. Nothing more sophisticated than that. The intercomparison that we did demonstrated that with confidence that they were all measuring the same thing, so there was no reason to favour or unfavour any of the particular techniques.
Further questions? I have one really short one. You said 2 to 3 times more certain. What does that mean?
Well, that just means that the uncertainty range is 2 to 3 times smaller.
Okay. Thank you, Andrew. And here we welcome the next speaker. We did not figure out the first name yet, but it's Mr. Leonard.
Hi, welcome everyone. You just heard that Greenland and Antarctica are experiencing increased mass loss, but there are other regions in the world that have been experiencing dramatic changes as well. And I will point out one of them, the Canadian Arctic. Sorry. So the Canadian Arctic is usually split in 2 parts, the northern part and the southern part. I denote them as NCAA and SCAA. The northern part has about 100,000 square kilometers of ice, whereas the southern part has like 40% of that, 41,000 square kilometers. And a large tundra area also, where a lot of seasonal snow accumulates. I will come back to that. So why is this region so interesting? Actually, there is a very nice paper of Alex Gardner that appeared in Nature last year. And these guys, they show that there was an increasing mass loss during the period 2003 to 2009, both in the northern part and in the southern part. Combined about 350 gigatons. And what you can also see here in the left plots, is that there is a good agreement between 3 different techniques. And one of them is the SMB plus discharge technique. And you can see that it was only applied on the northern part because that was the only region where they had reliable measurements to validate our model. Another issue with this study is that the period is relatively short. So we were wondering how this recent mass loss is compared to the longer-term mass. Okay, so that's my research question, the longer-term perspective, and my second research question is actually to estimate what the future would be of these Canadian Arctic archipelago glaciers. The key point here I want to make is that the mass balance of this region is really dominated by SMB because the calving is assumed to be relatively small and also isolated only in the northern part. So the SMB for this region is really only what comes in, being precipitation, and what goes out, surface runoff. We used our regional climate model, RACMO. We forced it with ECMWF reanalyses, and we evaluated the model by GRACE and in situ measurements. I won't go into the in situ measurements today due to the lack of time, but I will show the GRACE results. And then for the future, we of course need a GCM to force our model at the lateral boundaries. We used the HM2 model because it was the most reliable in terms of large-scale circulation. Okay, so this is the first result. You can see the mean surface mass balance of the period 1960 to 2011, so 52 years average. On the left, you can see the northern part. On the right, the southern part. And you can see what you expect, of course. We see accumulation on top of the ice caps and ablation at the edges. Of course, this is 11-kilometer resolution, which could be a little bit crude for resolving the smaller glaciers. So what we did, we compared hypsometry from our model to the observed hypsometry from a DEM, and we corrected our SMB by comparing these. And it's actually a relatively small correction, only a few gigatons per year. So that allows us to compare our SMB plus the calving of 5 gigatons per year in the northern part with the GRACE time series on a monthly time resolution. And that's what you see here in blue, the GRACE data from 2003 to just September of this year, compared to RACMO output in green, which only shows the ice caps, so only the glaciarized areas, and in red, including the seasonal snow. And what you first can see, of course, is this increasing mass loss. So whereas the first years were actually relatively in mass balance, we can see this increasing mass loss from 2005 onwards. And also 2012 was again a spectacular year, so very comparable to the years before of around 100 gigatons of mass loss. So if you compare the trend in both, it's actually very well agreeing of the mass loss about 69 gigatons per year, which is actually the same number as the Antarctic mass loss currently. So it's a very interesting region, that's for sure. Another thing is that if you look at the amplitude of the seasonal cycle, in GRACE it's very, very large actually, and that is explained because in the GRACE solutions you don't only see glaciers, but you also see the seasonal snow, and that's what we also can see in our model in the red curve. So there's a seasonal cycle which is explained by the seasonal snow. Okay, so this is the longer-term surface mass balance from our model 1960 to 2011. The northern part was actually, the SMB was near zero before 2000, so any mass loss from the northern part is presumably related to calving. And then you can see after 2000 this sharp decrease of SMB, whereas actually the southern part was already losing surface mass before 2000 of around -10, -15 gigatons per year, and you can see a small decrease afterwards. And these estimates from the southern part actually agree very well with the recent remote sense-based estimates. Okay, so this is actually the same figure. The blue lines is the same what you just saw, but then I also plotted the results from the GCM forest run. You can see in red, so you can see that actually the GCM forced SMB is a little bit on the low side compared to the reanalyses, because the GCM was slightly too warm, so the SMB is underestimated. But actually, if you look at the time window 2000 to 2010, it's very comparable for both. And then what you can see also is that the SMB becomes increasingly negative in both regions, but also that the focus moves from the southern part towards the northern part. Okay, and I want to focus a little on the SMB components. We can distinguish all components, and that's what you see on the top left. I plotted them accumulated over the entire period as a function of the total volume of the CAA as a percentage. And you can see in pink the runoff, which is equivalent to around 30% of the volume in 2100. You can see the green line, it's actually, oh sorry, I was wrong. This is melt in pink and green and runoff. You can see that they're very close to each other, which means that the refreezing potential, which is shown in red, is very limited in this region. And also that snowfall does not compensate the increase in runoff, only for 30% or so. And the SMB shown in black is around equivalent to around 80% in 2100. So around 80% of the volume is lost by a surface mass loss. Okay, and then on the right you can see we use this because the SMB in this region is very sensitive to summer near-surface temperatures. So we use this relation between summer temperature and SMB to extrapolate it to the entire CMIP5 ensembles. And then that you can see in the right figure as box plots. So for different scenarios, 2.6, 4.5, 8.5, and the average mass loss in the 21st century is around 200 to 250 gigatons. What you can also see that there are very few ensemble members that actually predict a positive SMB. Lower than 1% of the scenarios does that. So we can safely assume that the mass loss will persist in the next century and probably beyond. But I want to say that, of course, we don't include any changes in discharge, and we don't have the mass balance elevation feedback, which could be important on the longer timescales. Okay, so one slide to go to show what the driving mechanisms could be of this mass loss. On the right side, you can see the energy available for melt on the CAA glaciers in black, increasing from around 40 watts per square meter to 80, so a doubling in the time period. And in green, it shows the shortwave contribution to the melt. And you can see that actually it increases at the same rate. So that means that actually the albedo on the glaciers is the driving mechanism. So the decrease of albedo, which increases the availability of shortwave energy to melt the glacier surface, while the other components are less important. On the left, you can see that not only on the glaciers, but also in the surrounding tundra and also on the sea ice, there is a great decrease of the length of the snow-covered season or sea ice-covered season with 30 to 60 days. So not only on the glaciers, but also on the surrounding terrain, the albedo is decreasing, and that enhances the mass loss. Okay, this brings me to my conclusions. This is the first time to apply a regional climate model to a non-ice sheet region. The results compare well with GRACE and with the local measurements. The GRACE solutions that we have shown, they contain a signal from the seasonal snow, and the mass loss from the CAA region will persist throughout the 21st century and probably beyond with enhancing warming. Thanks.
Thank you very much, Jan. He did leave a few seconds for questions, so I hope there's a quick question for Jan. Bob?
Any idea why the GRACE results just are about 10% behind
We just plotted them. You can plot them wherever you want because it's anomaly, so it doesn't matter. We just plotted them to see the difference. Otherwise, yeah.
Thanks very much, Jan.
Yes.
I do want to move on to the next talk, which is going to be given by Cody Biedlow, and it's going to be moving from Canada over to the neighbor to the west, Alaska, talking about Alaskan glaciers. Can you back up one?
All right, thank you. My name's Andrew Cody Biedlow, and I'm going to be talking today about the projections of 21st century contribution of Alaskan glaciers to rising sea level. So Alaskan glaciers cover approximately 12% of the global glaciarized area outside of the ice sheets of Antarctica and Greenland, and they have also been identified to be a major regional contributor to sea level rise. Radix and Hawk 2011 showed that Alaskan glaciers may lose up to 25 to 60% of their volume by the end of the 21st century. So the objectives of this study is to project the volume changes of all Alaskan glaciers through the 21st century. And so what we're doing is we're taking off from the Radix and Hawk 2011 study, and we are looking at 14 GCMs from the AR5 running under two emission scenarios, the RCP 4.5, which is kind of a middle range, and then the 8.5, which is a higher range scenario. Like Radix and Hawk 2011, we also use a half-degree monthly temperature and precipitation from ERA 40. But in addition, we're also using 2 kilometer by 2 kilometer high-resolution monthly gridded temperature and precipitation data. One of the biggest differences from the previous study and this current study is that we now have a complete glacier inventory for Alaska, and there's the link below to the GLIMS RGI website where you can download those data. So looking at the Alaskan glacier inventory, this is from the Randolph Glacier Inventory version 2.0. These are the glaciarized regions in Alaska in red. So we have a little over 26,000 glaciers, around 89,000 square kilometers of ice area with a volume of about 28,000 cubic kilometers. And so what we do is we take those data and we input them into this elevation-dependent mass balance model for projecting regional glacier volume changes, and we apply it to every single glacier within that inventory. This is the same model that was used in Radix and Hawk 2011. And our inputs are monthly temperature and precipitation. And then we calibrate those model outputs to mass balance observations, both on the sub-regional average balances as well as individual glacier mass balances. And then for future projections, we also use volume area length scaling to account for geometry changes. So what we do is we plug in these 14 different GCMs, as I mentioned earlier, into the mass balance model. So what we have here are just time series of the RCP 4.5 and 8.5 GCMs with the mean annual temperature on the top and the mean annual precipitation on the bottom for all 14 GCMs. We also have the individual GCMs listed in their country of origin below. So we take those forcings and we put them into the mass balance model and project them into the 21st century. And so these are the outputs from the elevation-dependent temperature index model. So on the left here we have the RCP 4.5 volume time series from each of those individual 14 GCMs. And then on the right we have the volume projections for the RCP 8.5 for each of the GCMs. And so what we get here is a volume change for the RCP 4.5 emission scenario of about 9 to 37% with a mean around 25%. And then for the RCP 8.5 scenario, we have a volume change percentage of 17 to 49% with a mean around 37. So we get quite a bit of spread for both emission scenarios. So one of the calculations that were done, we used with ERA 40, which has pretty coarse spatial grids, half degree by half degree. And upon further investigation, we found that they fail to represent the spatial variability of temperature and precipitation found at the subgrid resolutions. So in response, we wanted to implement a higher resolution temperature and precipitation data, so we turned to Oregon State University's Hill and Kalos 2012 2 kilometer by 2 kilometer monthly temperature and precipitation. They calculated these temperature and precipitation grids using extensive weather station data and then synthesized those data to existing climatological norms from 1961 to 2009. So just the figures on the right there are just the mean monthly temperatures from 61 to 2009 on the top, and then we just have a map of the mean monthly precipitation from 1961 to 2009 from these data sets. So if we just zoom in, just want to do a quick comparison between the Hill data set at the 2 kilometer by 2 kilometer resolution and compare it to the previous ERA 40 half degree by half degree resolution. You can see over here with the plots on the left that the ERA 40 is quite a bit coarser, and we don't have as good a spatial representation as we do with the Hill data on the top here, the 2 kilometer by 2 kilometer. So the grids are actually, the climate grids are represented by the blue dots, and the individual glaciers from the inventory are represented by the red little crosses. And this is a zoomed in area of the Kenai Peninsula, just to kind of give you an example of what kind of spatial representation that we're getting with these different data sets. So we run the Hill data set through the model as well from 1963 to 2009. We just did a little comparison with the runs with the ERA 40 data set. We held all the parameter values constant between the two different data sets, and the only thing we did adjust was the bias correction between the temperature from the climate data and the highest altitude of the glacier, and that was our tuning parameter. And as you can see from these simulations that we do get a little bit more volume loss with the Hill data set, as well as a longer time period for model runs, since we ran from 1961 to 2009. In contrast to previous studies, we wanted to look at some of the mass balance observations on the individual scale and compare the model with the observed. So fortunately in Alaska, we have two benchmark glaciers by the USGS. So we have the Golcana Glacier pictured on the top here, and we also have the Wolverine Glacier pictured on the bottom, which have a really good, nice, long observed record from the 1960s to 2009. So one thing we did with the model, just to kind of do a quick validation and comparison, is we took the mean mass balance profiles from the model as well as the observed data and just kind of compared them. So these are mass balance plotted with elevation, so you can see the mass balance profiles. So on the top here we have the Golcana Glacier, and I plotted the Hill data run with in blue. The observed is in black, and then the ERA 40 is in red. And as you can see for the Golcana Glacier, we don't get a really good representation. Wolverine Glacier, on the other hand, on the lower plot here, we get a little bit better representation with mass balance with elevation, especially in the lower regions of the glacier. However, things start to break down a little bit as we move up in elevation. Continuing our kind of point mass balance comparisons, we also, on Wolverine and Golcana Glacier, we have temperature records that also span from 1966 to 2009, which are really nice to compare with our Hill temperature data. So what we did is we found the Hill temperature data that's in the same location as the observed weather station, and we looked at just a quick comparison between Golcana and Wolverine Glacier. And as you can see, the observed station data is in red, and then the Hill temperature is in blue, and then we did a little correction because the actual grid cell is slightly higher in elevation than the actual observation elevation. So we did a little lapse correction there, and they end up working out looking pretty close to each other. On the bottom here we have, again, observations versus model output, but now we're looking at the annual balances and scatter plots here. So we have the Golcana Glacier here on the left, where we have the model plotted with the observed annual balances. The red is the ERA 40 and the blue is the Hill data. And again, with coinciding with the previous slide, that we don't have the greatest representation on the Golcana Glacier. But when we move over to the Wolverine Glacier, we're getting a little bit better agreement between the model and the observed. So here's some kind of drawing conclusions we have from these analyses, is that the future projections are highly variable depending on the GCM and the emission scenario. We have a volume loss range of 9 to 49% with a mean around 21% for all GCMs in both emissions scenario. The Hill data and the ERA give significantly different results for the calibration period from the 1960s to 2009. Some glaciers show good observed model agreement while others don't. And that we've also found that these point mass balance observations are valuable for model calibration and validation, but one cannot expect a perfect agreement on the individual scale, especially since this model was originally designed for looking at mass changes on a regional and global scale, and it's not really designed for looking at individual glacier balances. So I have some future work ahead of me. I want to expand the model and utilize available stake measurements for calibration, which is currently in progress right now. I want to continue to find stake measurements for Alaska, and I'm currently compiling kind of an extended version of the stake measurement data set that we have for Alaska. So if you do have any stake data for Alaska, please notify me or let me know. Talk to me afterwards. I'm always looking for data that I can help validate and calibrate the model. Furthermore, I want to revise the calibration with all available mass balance data and then possibly use transient snowline data from satellite imagery. And then, of course, we want to rerun those 21st century simulations at the 2 kilometer by 2 kilometer climate grid resolution. So as I mentioned before, so if you do have any stake data, please let me know. There's my email address up there, or you can talk to me after this session. Thank you.
Yeah, here we go.
Well, the nice thing with stakes is that we can look at the mass balance gradients with elevation, and so we can kind of get a good idea of what's going on in the accumulation and the ablation area, and that's really the target that we want to shoot with that.
If there are no further questions, then thank you, Andrew. And we'll move on to Andy Ashwaden. We're moving now on to the Greenland part of the session, which will then be followed by a whole ice sheet approach and then one Antarctica talk. Andy, thank you. Because it works, right?
Yep. Yeah. I checked it in the morning, it worked. There are no animations, nothing fancy in there.
I don't know.
Can you open it in preview, maybe, instead of distiller or reader? Uh-oh.
So that it doesn't take all the time.
The AV person.
Is there someone? So how does one kill something in Mac?
I can't really see the mouse. No, where's the mouse?
Do you have a PC version?
I don't know how to kill things in Mac, so that's who knows.
Whoops. That's a PDF file. That's a PDF file. That's not the actual file. Do you have a version of it here in PC?
No,
It's supposed to be a PDF.
it's just a PDF. That's a PDF, and it's the right size.
If we don't have a quick solution, we can just put you at the end,
Get someone else.
and then it gives us
Yeah.
some time for Andy to get his talk.
Okay, so we move on. We'll have Andy's talk at the end, so that we have some time to sort this out. Marco is going to be next, and I hope he's around, and he is not. So we'll, that is interesting. So, in preview, how do you do that? Yeah.
There's no right click.
There's, how do you do right click with a mouse? I'm a theoretical physicist.
Of course, now I haven't got my glasses on.
Right down, right down.
Now we're talking.
If Tad was giving a talk, I'd give him 2 more minutes.
And I'm giving 2 minutes less, so I have to hurry.
There you go.
Okay. Okay, I'll try to be quick. Sorry for that. Today I would like to present some work I've been doing with Jan van Angelen from the Utrecht University. I'll be talking about Greenland mass changes from 1960 to 2000. And since this is the sea level rise session, I guess I'm supposed to give you a number of sea level rise from Greenland. I've decided to start with my number and spend the following slides trying to explain why I think we should take this number or these numbers with a grain of salt. I've used the parallel ice sheet model, and PISM has been forced with RACMO data and an RCP 4.5 emission scenario. I'm plotting here 2 different realizations, and one of them roughly gives 8 centimeters mass loss by the end of the 21st century, versus the other one arrives at a mass loss of approximately 10 centimeters. These numbers are not that crazy. Helsen and others on Monday or Tuesday had a poster using a similar type of forcing but a different ice sheet model and came up with relatively similar numbers. While that still doesn't mean we're getting the right answer, we still may get the wrong answer for different reasons, or maybe even the same reasons. Anyway, the question is why I'm plotting 2 different realizations, and that's what I would like to explain in the next couple of slides. The traditional way of initializing an ice sheet model used to be you just take an initialization techniques that could be data assimilation or various types of spin-ups. You take that initialized ice sheet and you run your forecast. Here I'm proposing a slightly different approach with an intermediate step. It's called Hindcasting. So you initialize your ice sheet model the same way, and then you do the hindcast, and after that you take the output of the hindcast and you run your forecast. I've not come up with this idea, just stole it from global climate modeling or coupled ocean atmosphere modeling. And for those of you who are not that familiar, hindcast is sort of a way of testing your model. You use known or closely estimate parameters, you throw it into the model, and then you compare the model output to observations. So we initialize the ice sheet model with mean values of 2-meter air temperatures and climatic mass balance that I got from RACMO. And here we have 2 different realizations. We have mean values of the error reanalysis done with RACMO and of another forcing done with HGM2 forcing for a slightly different time period. That's the initialization. In the hindcast, we take the initialized ice sheet model and we force it with monthly time series of, again, temperature and climatic mass balance. And here we take the monthly time series from the error reanalysis and from HGM2. Now the forecast is similar. You take the hindcast output and you drive it with RACMO data with HGM2 forcing from an RCP 4.5 scenario. For the HM2 forcing, that we can apply directly, but if we want to apply or use the error reanalysis data, we have to create anomalies. And that's basically the only difference that we use in our two different simulations. So let's look at the recent history. Let's do some model validation. The nice thing about the Hindcast is that it covers an area where we have extensive in situ and remotely sensed observations. For example, we have mean flow speeds from SAR. I've presented such figures in other talks. I'm going to skip over that. Another way of validating your model is using cumulative mass changes from GRACE, or very interesting are elevation changes, for example, from GRACE or from ICET. In my talk, I will focus on GRACE, and in the end, I'll have one slide, due to time limitations, comparing with ICET. Okay, we look at mass changes from 1971 until 2009. And we have the two realizations. One is the ERA interim initialization, the other one is the HM2 initialization. And for the years 2004 to 2010, we have GRACE data where we can compare the total cumulative mass change. And as you can see, both realizations, both our ice sheet model realizations or simulations, get the trend that GRACE sees quite right. One almost gets it magically or perfectly right, and the other one is slightly off. So is this a perfect fit? Well, let's look at something else. Let's look at ice discharge at the ice-ocean interface. We have an estimate from Van der Broeke for the area, or for the time around 1996, and he gets roughly 450 gigatons from observations. Well, our two models are not that bad. They get the background discharge in the right order of magnitude. Error initialization gets it almost right, and HM2 underestimates it slightly. However, from observations, we know that ice discharge has increased after 1996. However, this is not simulated in our model. Our simulated ice discharge remains constant. So, wait a minute. We know, again, from Van der Broeke that mass changes between 2000 and 2008 are equally split between changes in surface mass balance and ice discharge. However, as I explained in the previous slide, we don't simulate a change in ice discharge. Therefore, the ice sheet model should only produce half of the mass loss that it actually does. So why do we get such a good agreement with observed mass loss? Well, I don't want to go into too much detail. There is not much time. But the bottom line is that we have to do a careful validation. By just looking at GRACE or just looking at the scalar time series, we can still get it right, but for the wrong reason. A better metric to use are surface elevation changes. And here on the left, we have ICET surface elevation changes from 2003 until 2009. And in the middle and on the right, we have the two different initializations. One is the ERA initialization, and the other one is from HM2. And now we can see we get too much mass loss around the perimeter. And that probably leads to the fact that we get the trend right. So we produce too much mass loss, which has not been observed. And why that is exactly the case, we have to look a bit deeper into that. I can't give you a definite answer yet. Okay, I already come to my conclusions. First, despite that the ERA and the HM initializations show very similar mass loss over the GRACE epoch, the mass loss trends by the end of the 21st century differ by around 2 centimeters. And this is the result of having different initial states. While the climatic mass balance shows a similar behavior for both simulations, it's the actual discharge that differs between the two different initializations. And that again reiterates that we have to get the dynamics of the ice sheet right to get the discharge right. Second conclusion slides. I think it's very worthwhile switching from just initializing the ice sheet and then doing a forecast to initializing the ice sheet, then doing a hindcast, compare with observations, validate your model before you start your forecast. And with this, we can actually measure the sensitivity of our model to initial states. And here for comparison, for simplicity, I've only shown an error initialization, a HM2 initialization with RACMO. Of course, you can do that with other regional climate model forcings as well. And therefore, we're only subsampling the real sensitivity by showing two numbers or two simulations. Yep, that's all I had to say. Thanks.
Thanks very much, Andy. Are there questions for Andy? We have.
You didn't put ocean forcing, did you?
Nope, I didn't.
So then you can't really hindcast all of them, but that's what you said. You can't really hindcast the entire ice loss of Greenland.
Yeah, I can't simulate the speed up that we observe, which is most likely due to changes in ocean conditions. So I have to leave that out for now.
Is there the intention to add it in later?
Well, if someone comes up with a good theory and tells me how to implement that, then we'd be happy to do that. But as far as I know, there's no theory that can be easily put into a whole ice sheet modeler. Lots of studies have been done looking at flow line modelings and tweaking and tuning and getting the right result. But I think we're not yet there to implement that or couple that with ocean models and get the right result. But we're making progress.
Any last question for Andy? All righty. Thank you very much, Andy. And we'll move on to the next speaker, who's Marco Tedesco. And he'll be talking about Greenland, measurements and projections.
Thanks, Bob. Hello, everybody. So I'm going to talk about one knowledge Xavier Fetwise is co-author on this study, and other people who contributed to the 2012 records data. I'm going to go briefly through some of the results we updated, and then show some future projections and try to link the two things so that things look consistent, even initially they might not look like. This was basically, we have this analysis paper published now on the Cryospheric discussion accepted. So if you want to go for more information about the data or other analysis, you can go there. It's an open access journal. Bottom line, 2012 was really a huge year for many records that were set. Actually, everything we looked into was a new record. So it was a kind of funny, in a sarcastic way, thing to do. Of course, the melt extent, we've been hearing a lot about it. The melt duration for some areas was up to 2 months longer than the average, especially over here and over a northwest part. Satellite estimates land surface temperature, ice surface temperature, and albedo set a new record for this time period. The total mass balance from GRIS set a new period. These are some of the figures that you find on the paper, and this is the trend for the MODIS IST. If you look, basically the mean average for Greenland was -5.5. This is the June, July, and August mean temperature. If you look at the melting index, is something we used to quantify from PISM and RACMO2 data. The strength of melting season is in two different approaches, one by myself and one by Tom Mote, is about 2.2 standard deviations above the mean. If you look at the model surface mass balance, this is where it falls by the MAR model. And if you look at the GRACE data by John Ward, this is where it goes. Actually, it was the biggest change during the summer and also the biggest annual change since the GRIS data. But again, you can go to the Cryospheric discussion, and we also identify some of the drivers, mostly the now very popular albedo feedback mechanism kicking in, and also the atmospheric drivers, which I'm going back at the end in a second. The MAR model is very popular nowadays, but and is very similar to RACMO2. We heard a lot about it. What you do, you really force the boundaries, a larger area of boundaries with the ECNWF, in this case, data, and then you have a much higher spatial resolution grid where your atmospheric model propagates your atmospheric parameters, and then it's coupled, fully coupled with the snow model that resolves the entire energy balance. You have about 20 or more layers within the snowpack, and then it's a fully coupled model. So what we did actually with Xavier was to replace some of the ERA interim and ECNWF forcing data with outputs from GCMs, and exactly what we took 3 of the CM5 model scenarios, models, and we considered 2 of the RCP scenarios. So RCP 45, it's a relatively moderate, not very aggressive, but still still 850 parts per million CO2 by 2100, and then a more aggressive scenario. And the 3 models are the Canadian Earth System model, CANES2, the Norwegian Community Earth System model, and the model for the MIRC 5 from Japan. Actually, Xavier does have, we do have another paper on the cryosphere that is looking at the single surface energy balance components through this. What we did actually, we focused on dissecting the results on different drainage basin for Greenland. So we have a drainage going from 1 to 6. These are slightly different from the ones that Eric Renaud or other people are doing. Of course, we have to match the same mass to make more consistent results. But overall, one thing that we did is we took the 1980, 1999 surface mass balance values, and you can compare this one's the ERA interim, which is our truth. Even it's basically what we use to study current scenario, and then you compare the mean and the variability and the standard deviation of using the 3 different models, and this is for the historical period, so 1980 through 1999. There is some variability among the different models. This is done for the 6 different basins overall. So this is due mostly to the sensitivity of the different GCMs are providing to forcing of the MAR, because of course we use the same model to force things. So this are not the happiest graphs to show in this case, but bottom line, this is runoff. One thing that we did, because you do have different GCMs, you have different sensitivity to how of course from the outputs of the GCMs that you feed MAR with, we thought to homogenize things by plotting all our results and looking at as a function of the global surface temperature anomaly that each GCM is telling us. So rather than having plots and everything else, what we thought, what is the runoff, projected runoff, rather than plotting versus a time, what is the projected runoff as a function of the global expected increase temperature, basically. And so these are the plots that you see. This is done for the different scenarios, RCP 45 and 85, and you will see different, this is done for the albedo. On the paper, we actually, that was accepted on ERL a few weeks ago. You will find all the plots, and also in the supplementary material you'll find some analysis of the precipitation and other parameters. Bottom line, we find that you have an increase in precipitation due to increased moisture, but overall on a long term the increase in runoff for all basins is really exceeding the increase in accumulation, and so that is of course resulting in a negative in decreasing, basically increasing runoff and decreasing surface mass balance. So the albedo is really interesting because you see that the scale is the same, it's absolute value for all basins. This goes from 1 to 3, and so they go from north, and you go on the east coast, and then you go again on the south, and then you go on the west, and then you go back northwest. But the change is really in the north part, and which is the basin number 1, this one on the top. and on number 5, which is the southwest, are really the most dramatic, both in terms of albedo and also runoff. So if you look at the surface mass balance, these are the plots, we wanted to actually look at what is the global surface temperature anomaly when you might start having negative surface mass balance. Now, because each model realization, forcing with a different GCM, is sensitive to how the GCM are sensitive to the CO2 scenarios, you can't really say, there are biases, of course. So what we did, the line that you see here, it's really the mean surface mass balance for the 1980-1999 period. So what we looked into are actually the global surface temperature anomaly, where when you might have that the surface mass balance projected is below the mean, and of course because it's starting to decrease again, that's close to when you might start having potentially negative surface mass balance. So it's really not telling you when the surface mass balance negative is starting, but it's telling you an indication where you start having below mean and then moving toward negative values. And so basin 1 is aggressively starting for a very relatively low global TAS value. Some models, some realizations they hit and some others they don't suggest that this will happen for other basins. This is a table showing you the temperature range for the global TAS, the surface temperature anomaly, where for each basin you do have the condition when the surface mass balance is below the mean, and where you don't see results is when it didn't happen for those cases. So you see that for basin number 1 and basin number 5, which are again this one and this one, you really see that all realizations suggest a range of most of all realizations suggest a situation where you will have that the surface mass balance will go below and very likely become negative. And the temperature range, for instance, for basin number 1 and 5, it goes from 0.64 in the case of a Canadian for relatively moderate RCP 45, or 0.6 in this case, through 1 to about 2 degrees. And in the case of the basin number 5, this goes, values for the minimum condition realization is probably 0.67, similar to the other one, but the maximum value is slightly higher. Basin number 4, which is about here, around here, it doesn't really see a lot of these conditions, a lot because of the increase in accumulation in the area. And one thing that I want to point out that, of course, I can't show here, but you will see in the paper is that a lot of the changes in the surface mass balance are due to the switch from frozen to liquid precipitation, and that was, according to the projections, driving a lot of increased runoff and losses. So if you translate that in sea level rise, as somebody was saying, I need to have a sea level rise, right? This is basically the range for the different basins, for the different model. The lowest value, the minimum value here is the one obtained with the RCP 45 case, and the upper is the RCP 85. And these are the 3 realizations for the 6 different basins. Again, this is are the conclusions. Basically, I was mentioning the basins. What I want to point out in the last minute that I have is that the projections are likely underestimating the projected sea level or whatever surface mass balance anomalies, because the model currently does not account for the topographic change effect. So that's something that we need to include, and of course the ice dynamics. But and also to go back to what I was telling you for the 2012. We found that about 50% of the 2012 melting runoff and surface mass balance anomaly record can be explained through the negative NAO and southerly air flowing from south. This has been persistent for the past years, starting in 2007, and none of the SIMIFY model is actually simulating this. It's predicting this. So all the results that we see are actually not projected, even for 2005 or so on, including that effect. And you will find the comparison with the results. But this also is another reason why the results are underestimating some of the effect that projected, so even in the short-term range. More on the Cryospheric discussion and ERL. And I hit the 0 seconds. Thank you very much. Thanks a lot.
So Marco doesn't take any questions. I'm kidding. No, but we don't have time for questions, but he'll be around, obviously. So the next speaker is Olivier. Yes. Here he goes.
It's a Mac, right?
Yeah.
Okay.
Good afternoon, everybody. I will present some results that have been obtained at LGGE in France using two models to forecast the future of the Greenland. And this work was performed in the framework of the European Ice-to-Sea project. I will go very fast on this. Since the last report of IPCC, we have developed, and I think we have seen emerge a new generation of ice sheet model. And in the framework of the Ice-to-Sea project, the purpose was to run a number of models and to compare their results for a given scenario. Here, I will not present the whole set of models that have been used in Ice-to-Sea. I will just focus on two of them, Elmer Ice and GRISLI. And the first thing I will do is to see the difference and the feature of these two models. So Elmer Ice here and GRISLI here. So Elmer Ice is a full stocks, whereas GRISLI solved for the shallow ice and shallow shelf approximation. Elmer Ice is finite element, GRISLI is finite difference. Elmer Ice is unstructured mesh from 30 kilometers in the interior to 1 kilometer on the outlet, whereas GRISLI is a structured grid of 5 kilometers. On the margin, at the boundary condition with the ocean, it's fixed in Elmer at that time, and where it's moving in GRISLI. And for the land-terminated glacier, we can accept retreat only at that time in Elmer, and it's moving freely within GRISLI. Temperature field is fixed in Elmer, where it's computed in GRISLI. And for the modelization, initialization, we will see that it's very important, and we are doing very similar thing to initialize the model here. So we do inverse method to infer the sliding coefficient at the base of Greenland, and we use observe surface elevation and surface velocity to do this. For GRISLI, the sliding, we first start from the sliding coefficient computed by Elmer, and it's refined, it's modified a little bit from observed surface elevation and balance flux instead of observed velocity. And for both models, we do perform a relaxation of the surface for 50 years within Elmer and 200 years in GRISLI. So I think you know all about this model now. You know all the difference. So they are very different models, and we'll see how they behave. The first thing I will show is velocity after the initialization. That means after inversion of the basal drag and relaxation. So here are the data we are using for the inversion, and here are the results with Elmer Ice, and here are the results for GRISLI, and it looks very similar at this when we are looking at this from this side. If we zoom, for example, here we make a zoom on the west coast near the Jakobshavn glacier. Again, here it's the data, here it's the Elmer Ice result, here is the GRISLI. We can see that Elmer Ice is capable of capturing more precisely the small outlet on the west coast. If now I go on the east coast of Greenland, from Elheim to Gangalusuk glacier, it's even better for Elmer Ice than for GRISLI, which is quite patchy here. But you can see if you go even further in detail that there are some very small, for example, this small glacier here that is not that cannot be seen in Elmer ice. So we will need to go with a further thinner resolution to capture this smaller glacier. Okay, so now I'm doing a comparison for 4 flow lines. So this is the white line here, and the first flow line is along Jacobshaven Glacier, Cryospheric for this one, Helheim Glacier, and this small glacier, Russell Glacier, which is a small glacier, land-terminated glacier. So take care that the vertical axis, so it's the speed, the flow velocity is very different. Here it's hundreds of meters, here it's thousands of meters. So observations are in black, Elmer is in blue, GRISLI is in green, and we can see that Elmer is capable of reproducing the velocity of this fast-flowing glacier, and I think it's one of the first time that a large-scale Greenland model is capable to reproduce this kind of velocity profile for the whole continent. Okay, so this was for the initialization, and now I'm moving for the forecast, for the prognostic simulation. So I will run both models for 200 years, from 2000 to 2200, and I will use the IPCC E1b scenario, and the surface mass balance will be given by the MAR model, and there is no feedback. I will show, as a last presentation, feedback between surface mass balance and elevation, but for this first application, there is no feedback between elevation and surface mass balance. And as a reference surface mass balance, we use MAR forced by the ERA interim reanalysis. And then I will only use surface anomaly from MAR forced by this GCM here, ECAM5. Okay, and so let's go see what's happened. So here I'm showing the difference between the 2200 and the 2000 year. So it's a difference. So it's different in surface elevation and it's different in flow speed. So what we can see for the surface elevation that we have thinning on the margin of the Greenland, especially on the west coast and the north, and thickening, small thickening of on the interior. For the velocity, we have a strong decrease of the velocity on the margin, and increase of the velocity further upstream of the margin, and because of the increase of the slope of the ice sheet. And what we can see is that both models give the two models give very similar patterns. Okay, and now I'm again looking at the 4 flow lines: Jacobshaven, Kangerlussuaq, Helheim, and Russell Glacier. And here I'm plotting. So it's difficult to read, but here it's difference in terms of surface velocity, speed. Okay, the first plot is surface velocity. The second plot is difference in surface elevation between 2200 and 2000. So again, blue is Elmer, green is GRISLI. And what we can see is that, for example, on Jacobshaven, we have an increase of the velocity, larger velocity in 2012, in 2200 than in 2000, but then a decrease, and the decrease of the velocity is more pronounced for Elmer than for GRISLI. And this is quite very similar on at least all these 3 ocean-terminated glaciers. And for the change in surface elevation, we have plotted also the surface mass balance anomaly, which will give the surface elevation without any dynamic of the model. And what we can see, for example, for Kangerlussuaq, it's quite interesting because without ice flow, the surface will have decreased by 200 meters, but because of the ice flow, it will almost stay at the same elevation because of ice flux coming and ice flux coming at the front of the glacier. So, because I have to give some number, it seems to. So I will give some number, but it's an interesting result. Maybe not very pedagogical result, but this is the. So this is year, and this is the contribution to sea level rise for both models. So Elmer in black, GRISLI in red here. And what we can see is that it's exactly the same. And it's the same for, obviously, for different reasons. We have a larger surface mass balance for Elmer, but the decrease of the ice discharge is also larger for Elmer, so at the end we have the same contribution to sea level rise 200 years after the simulation has started. And it's quite insensitive to which GCM we are using. I will, because I run out of time, I will go faster. And the last simulation I want to show you is when we account for a surface mass balance, when the surface mass balance is corrected from the change in surface elevation, and it's done very simply here by adding this correcting term, and just very fast. So what we can see is that we have an additional thinning of the margin, so there is a positive feedback by taking into account this phenomena. The surface becomes lower, and so there is no more melt, so it becomes even smaller, etc. And so using this parametrization, we can produce some other number that are in the range of, that are a little bit larger than what I have just shown before, sorry. And conclusion, there's a lot of things to read, but maybe I can go just at the end. I think it's interesting to have the good velocity at the end of the ice stream, especially if we want to have moving margin and calving, if you want to take into account the calving at the front. Okay, thank you.
Is there any question for Olivier while I prepare the next slide? Michele?
These results I show. Oh, you were speaking about basal sliding. Here, the basal sliding is kept constant during the 200 years. So it's the basal sliding, the basal coefficient is kept constant. There are other simulations from I2C where the basal sliding is evolved as a function of the runoff, but I did not present this here.
Okay, thank you. Thanks. We move forward. Contribution of the surface mass balance of the Greenland sheet of the 21st sea level rise as simulated by global climate model CESM by Miran. Okay, thank you very much.
Okay, thank you. So here I want to acknowledge my colleagues at IMAU in the Netherlands, NCAR, and Los Alamos. Okay, so it is generally accepted that the global climate models cannot make a good job for the simulation of the surface mass balance of ice sheets due to climate biases and also due to the coarse resolution. A resolution of tens of kilometers is needed to properly resolve the surface mass balance of the Greenland ice sheet because there are very steep gradients of surface mass balance at the margins of the ice sheet. But here I'm going to show results of the community system model that includes atmosphere, ocean, land, sea ice, and now a new land ice component. And these results are comparable to regional climate models. And this success we attributed to a good climate simulation by the model, a sophisticated calculation of snow processes, including the evolution of albedo, and an adequate downscaling of the surface mass balance. So the calculation of the surface mass balance is done in the land module at a resolution of 1 degree with an energy balance scheme and at 10 fixed elevations. And then the surface mass balance is downscaled to the ICID model that has a resolution of 5 kilometers. For this downscaling, first a bilinear interpolation is done for the horizontal interpolation, and then a vertical interpolation is done between the different elevation models. We have, for the calculation of the surface mass balance, we have two systems. One is snow and the other one is ice. So the snow physics that are used in the land model for non-glaciated surfaces, for instance, over Siberia, are also used over the Greenland ice sheet. A maximum snow thickness is prescribed for the snowpack, and this is 1 meter. And when there is accumulation of snow over this 1 meter, we consider that we have a gain in the ice system. And when the thickness reaches 0, then we have ice loss. For the downscaling between the different elevations, only temperature and humidity are changing between the different elevation classes, while precipitation and radiation are kept fixed between the different levels. Temperatures follows a fixed lapse rate, and humidity follows the assumption that the relative humidity is constant between the different levels. For the calculation of the snow processes, the SNICAL model is used. And albedo in this model is a function of grain size, aerosols, the solar angle, and the model permits, so the model includes percolation and refreezing of meltwater. And the ice albedo is prescribed. So once we are melting this 1 meter of snow, we have a fixed albedo. So here we have results from 3 simulations, one pre-industrial one, then a historical simulation that includes insolation, aerosols and volcanoes as foreseen, and then a 21st century simulation following the pessimistic scenario 8.5, the RCP 8.5. So first I'm going to show you an exercise of evaluation of the model. I'm going to focus the comparison to RACMO2, but I will also compare the results to other regional climate models, and then I will go for the projections. So here you can see, so here you have maps of the incoming solar radiation at the land model, which has a resolution of almost 1 degree, and then for RACMO, and the same for the incoming long wave radiation. And here you have these scatter plots for which the resolution, the data from RACMO has been reduced to the same grid as the land model. So you can see that the correlation coefficient is good, it's 0.77. And the model is, CESM is slightly underestimating incoming short wave. This is the bias, so this is the difference between the means in CESM and RACMO. This is -3 for the net short wave, and for the incoming long wave we are overestimating when comparing to RACMO by 7 watts per square meter, and this is for the net 6. The correlation coefficient for the incoming long wave is this one here, so 0.92. And here we have the turbulent fluxes. So the correlation coefficient for the sensible is quite bad. It's very, very bad. And this is mainly due to problems in the tundra regions, because here we have points with partial ice sheet coverage. So there is a contribution from the tundra regions here. So when we take points which have only ice sheet, only ice sheet cover, so this in the blue points, then the correlation improves. And this is the correlation for the latent, the correlation coefficient for the latent heat flux. So here you have the biases, also for sensible and latent. So altogether comes to a very close number for the total budget. And here you have the maps of near surface temperature in CESM and RACMO for the summer. Well, I forgot to say that all of this is for the summer, June, July, August. So the correlation coefficient is very high, 0.98, and the model does a good job when we compare to RACMO, so we have a very similar simulation of temperature. So these are the maps of surface mass balance at the ice sheet grid, 5 kilometers, and from RACMO. So we can see that the bands of maximum precipitation here and here are well reproduced. We have higher precipitation in the interior than in RACMO, and we have lower precipitation at the high accumulation area here. The major ablation zones are well captured. The ablation area is 10% of the ice sheet, while it is 12% in RACMO, so pretty similar. In both models, we don't have an ablation zone at the southeast. And this is the correlation when we reduce the data to the same grid. And so we see that the system does not simulate the precipitation rates over 1,200 millimeters per year. So this is why you see this here. So the surface mass balance is pretty similar in our model and in RACMO. This is due to imparted compensation of higher precipitation and higher runoff in CESM. We have too much rain in the model. It's 15% of the total precipitation, which is out of range when comparing to other regional climate models. And this is sublimation. We are good. And refreezing is pretty similar, but in percentage it is much lower than in RACMO. So this is the evolution between 1850 and 2005. So we have significant trends for runoff, surface mass balance, and temperature. So for temperature is over the ice sheet is this 0.0086 Kelvin per year, and we have a surface mass balance increase in response to the Pinatubo eruption, so low melt rates in '92. So yeah, now going to the projections. So we have a global increase of 3.7 Kelvin under this scenario. For Greenland in summer is 4 Kelvin. And the highest warming is in the interior and the lowest at the melting, at the ablation areas. This is the evolution of melt and runoff surface mass balance. So the surface mass balance becomes negative by the end of the century. Precipitation is increasing by 35%. Snowfall is increasing by 18%. Surface melt doubles, and so does runoff. The increase in refreezing is quite small, and probably it is due to the fact that we have a limited refreezing capacity because we only can have 1 meter of snow. And This is the change in the surface mass balance map. So the ablation area is going from 9% to 28% of the ice sheet, and the equilibrium line is going 500 meters higher on average. The albedo change, so it's this, so it goes from 0.78 to 0.75, which represents a 12% increase in absorption of solar radiation. So mainly this increase is due to major exposure of bare ice at the margins. So in summary, so I think we have here the first GCM that simulates realistically the Greenland ice sheet surface mass balance. So our projections indicate 5.5 centimeters of sea level equivalent from the surface mass balance. We don't have the height feedback, of course. And so snowfall is increasing by 18% and surface melt is doubling. And the limitations are overestimation in the model. So we have overestimation of rainfall in the model, and we have a fixed thickness of the snowpack that is limiting the refreezing capacity. So yeah, that's 6 seconds.
Actually, she also did hit the zero counter on it. It's amazing, twice in the same session. Is there any question while I switch to another talk? Yeah, please, sorry.
Say again what your constraint is on refreezing, how the refreezing works.
So here there is no true snowpack model. So we have as maximum 1 meter of snow. So once this is melted, we are playing with the albedo of ice. We don't have snow anymore. So if we have 1 meter of snow, in reality we don't have 1 meter of snow. So we have the firn there, and so we have much more snow there holding the water, the meltwater. So the refreezing capacity is limited because from the fact that we only can have 1 meter of snow there instead of several meters.
Thanks. Next talk is given about Bob Binschengler. So I'm going to leave you with everything, and I'm going to switch you keyboards very quickly. So that it's a most practical thing.
All right, thank you very much, Marco. This talk and the next talk are going to focus on the results of a project called Searise, which stands for Sea Level Response to Ice Sheet Evolution. You can see on the right hand that a lot of people were involved in this project. It's worth noting that all of them, except those of us at NASA Goddard, volunteered their time. This was such an important project that we had to do this, and I'll get into that in a moment. I include NASA's logo because when we needed some support, Tom Wagner was there. He really championed the effort, and I thank him for that. You know how this story starts with the IPCC AR4. The quote from that report has already been given that indicated that there was a major weakness in being able to quantify future sea level because there weren't models that properly, incredibly incorporated ice sheet dynamic response to climate change. When that was discussed at a workshop held at Los Alamos National Lab in 2008, it was felt strongly that the community of ice sheet modelers simply had to come up with some response and some activity, some effort to provide some numbers for the next report, the AR5. And Searise emerged from that feeling that we had to do something. Ice to Sea was another effort you've already heard mentioned by Olivier. So with Ice to Sea, we had 10 different ice sheet models participated. 8 were able to run simulations for Greenland. 6 were able to run simulations for Antarctica. Obviously, some of those models were able to run both the ice sheet simulations. As I mentioned, this is independent of Ice to Sea, although there was a lot of communication between the two projects. What we did with Searise, what we started with after each model spun up or initialized, depending on which approach that particular model was designed to accept, was we ran a number of sensitivity experiments. We looked at the ice sheet in terms of being forced either from the surface through surface mass balance, or along the underside through the basal sliding parameterization, or at the perimeter. And the vulnerable perimeter obviously is the ocean interface with the ice sheet. So we ran a number of sensitivity experiments. You see how when I say under surface mass balance, 1 times AR4, that's the A1B scenario in terms of precipitation and temperature. We imposed that. We amplified it to 1.5 times that, and then amplified it again to 2 times those changes. We ran each of these experiments for 500 years. You see how we varied basal sliding. We doubled it 2.5 times and 3 times. And then ice shelf basal melting just prescribed melt rates underneath the ice shelves of 220 and 200 meters per year. Now, I note here that these are simple prescriptions. These were not trying to incorporate in these models process or relationships. We simply said, whatever your sliding is, double it. Whatever your sliding is, triple it, and move your mass around and just complete the run. So these were somewhat artificial in that sense, but they allowed us to test the sensitivity of the ice sheets as simulated by each of these models to these prescriptions. And we looked at the results in terms of the experiment minus the control. All these models would still have some changes going on even at the initialization time, which was January 1st, 2004. So they each ran a control, and so after they ran an experiment, we subtracted that control to try to isolate the response of the model to just that prescribed forcing. And that actually worked quite well. We tested that. And then I'll be focusing, in fact, Searise focuses more on the sea level contributions. So we're talking about the volume above flotation. So the ice shelves do not play into the volume changes I'll be reporting, nor does a lot of the volume lost from these deep marine basins in Antarctica in particular. It's just that contribution to sea level. And if you need a quick conversion to hold into your head, 4 times 10 to the 14th cubic meters is 1 meter of ice is 1 meter of global sea level. So just one example of the sensitivity results. This is for Greenland, and this is for the case where we doubled the sliding. And you see on the left-hand side how the different models responded to that prescription of forcing over the 500 years. And there is quite a range. You see it all color-coded there with a key on the right, various models, the names of which you might be familiar with. And that was all very interesting. The fact that we had such a large range was not a particular surprise. But what was a surprise when we looked at how the total volume change after 500 years for any given model when we doubled and then increased the sliding by 2.5 and then a factor of 3, it actually came out with a fairly linear relationship between as you increase that amplification factor, the volume of ice that was lost increased in a linear fashion, although each model had its own amplification to that linear response. But that was quite interesting. This characteristic I'll bring back into the presentation in a moment. So those were the single forcing experiments, but we also ran some combination experiments where we would do 2 things at the same time. Sophie in the next talk is going to talk a lot about this Greenland C1S1, which is just our shorthand for 1 time the AR4 A1B climate forcing plus doubling the sliding. So we did both at the same time. And we really didn't know if when we did that, we would get the same answer as if we just added the responses of those 2 individual forcing experiments. I honestly didn't think we would, because you can only lose a parcel of ice 1 time, and if you're going to lose it in both experiments, it wasn't going to be double counted in the combination experiment. But actually, I was quite surprised that when you did add up, just linearly superimpose those 2 individual forcing experiment results, you got almost the same answer as when you ran them in combination. And just the plot on the left shows how the change in the volume above flotation varied with the different models over 500 years. The plot on the right simply takes the ratio of the volume lost in the combination experiment divided by the sum of the volumes lost in the two individual experiments. And if it's identical, that ratio is 1. And you see that in almost all cases, we came within 5% of 1. So again, a fairly linear kind of response. We ran 3 different combination experiments for Antarctica with a similar result, that you could get quite close to the result of the combination experiment just by adding up the individual experiments that were combined in the combination. Well, that was all very interesting. We're having fun doing that, but then it actually was Anders that reminded us that that's not good enough for the IPCC, which was the motivation for us doing all of this work, that we had to get into their world, which was sort of dominated by these radiation concentration pathways, these RCPs. And this is just sort of a diagram that shows what some of those RCPs look like in terms of how the radiative forcing was prescribed to evolve over time, over that 500 years. So we had to get into this world. So we had to translate our forcings. We had our knobs, our climate knob, our surface mass balance knob, our basal sliding knob, and our ice shelf melting knob. And we had to convert that into what the RCP 8.5 looked like. And you see in the right sidebar here, just some shorthand for how we did that. Surface mass balance turned out to be the 1.5 A1B for 200 years, and then it modified a little bit. Sliding was a bit of a wild guess. Ice shelf melting, we went to a climate model and pulled out from the RCP 8.5 what the ocean temperature change would be, and then used the conversion from Jacobs and Rignot to a basal sliding rate, and only applied it to in Antarctica, only applied it to the Amundsen Sea and the Amory ice shelves, not to the Ross and the Ronnie. So anyways, we did that conversion. Here are the results from what we called the R8 experiments that corresponds as best we could to the RCP 8.5. And you see on the left, for Greenland, you see a meter arrow there for a 1 meter equivalent sea level rise. Quite a variety of responses. Some models sort of continued to lose mass at a faster and faster rate, others more stabilized. In Antarctica, again, quite a large range. And you see in numbers on the table on the lower part of this slide how we turned out for Greenland and Antarctica, as well as the range, which was considerable. Another comment I want to make here before I run out of time. Because of this linear characteristic, while these modelers were running their R8 experiments, I went back to the sensitivity experiments and I asked myself the question, can I predict what they're going to come out with? And so you see in these 2 plots here, for each model, 2 columns. The black column is what the model produced, and the multicolored column is what I predicted they would produce based on knowing what the sensitivities of the model are, of each model was to those 3 forcings. What was really nice about this was that up to 200 years, I could get really close to their answer. After 200 years, I couldn't. But what was also nice about the prediction was that we could then look at how much of their response was due to the surface mass balance change, how much was due to sliding, how much was due to the ice shelf melting. And you see that in Greenland, the majority of the response is due to the change in the surface mass balance, whereas in Antarctica, the majority is due to ice shelf melting. That was a major result there. It also says that the feedbacks are not a major factor in ice sheet contributions to sea level over like a 200-year time frame. But after that, probably the feedbacks are what was responsible for this technique not working. So 2 big results, just those results from the R8 scenario again. I wouldn't trust numbers out to 500 years, so I only showed them at 100 and 200 years. And this discovery that the linear combination of interpolations and single forcing sensitivity experiments are surprisingly good predictors for more complicated scenarios. So we can run just almost any scenario that we want with those 3 knobs. 2 big caveats. The models still have a lot of weaknesses to them. We need sound relationships for these processes. Admittedly, our prescriptions weren't very realistic, but we think the R8 simulation was better. And a big promise to you, the models are always getting better, so I think predictions are going to improve. Thanks.
I'd rather to move along. Thanks, Bob. Next talk is, for those of you who are here, we are running 10 minutes late, so we just came in, actually. So Sophie Novitsky, just going to go to the next talk. I'm going to switch keyboards very quickly, so
Great.
help me out.
Do you want me to?
Yeah, this is the juggling. Oh, below, under.
Below?
No, I go under. Okay, good.
Okay, so you're having the dance of,
I got it. Good.
of the keyboards.
Okay.
Right, so I guess I wouldn't be here today without the huge support of a lot of people in this room. And as Bob has already showed, the Searise paper have about 27 authors at the moment. But they're not the only one that I have to thank. Bob said also that it's true Tom Wagner supported us at Goddard a little bit. But there's also a lot of people in this room that helped Searise in many different ways that I've never thanked them really. And you could have helped Searise by, for example, contributing your data, or just by when we were talking to you in conferences and we would be throwing out presentations and you would tell us this is a lot of bollocks. So there is a lot of community effort behind Searise that we don't often acknowledge. So a lot of the additional information you can find, we have a Searise wiki and a few papers that are on the way. So the focus of my talk today, because Bob gave a fantastic introduction to Searise, I don't have to do this again. What I really enjoyed coming out of Searise is this concept of the linearity of responses. You saw this already in the curves, in the response of the curves that Bob showed you when we had the experiment where we were combining a climate experiment, an atmospheric forcing that was kind of dumping snow surface mass balance, and an enhanced sliding experiment. The response of that combined together, those scenarios, was very similar to if I'm adding up one climate evolution, atmospheric evolution, one sliding evolution. And so that was the total volume. And what I want to convince you today is that actually, if I'm looking at this patterns of thickness changes, again, it's a nearly one-to-one comparison. The reason for this is because the ice sheet responds very distinctly to a type of forcing that we apply, and that's what I want to go into. It's not very surprising as a result, but it has a lot of implications. Okay, sorry, I should have said that the aim of my talk is, this is the response after 100 years of simulations to a combination of my 8 ice sheet models that are taking part in Searise Greenland. The experiments that we are doing is the combination of the more snowfall, so the atmospheric experiments, and the enhanced sliding. What I want to demonstrate to you is that the signal here looks fairly complex. But if I look into more detail at my, but that signal basically has the fingerprint together of both my climate and my sliding. And that's basically the point that you want to take home today. Okay, so the climatic experiments, the atmospheric experiments that we are looking at is the lowest one that gives a mean contribution about 3 centimeters of sea level rise after 100 years. what the thickness change as a mean response for all of my climate model is this. You see what you expect in a way, because of what Maren showed you earlier on, is that the ice sheet has a lot of, basically it's going to thin where the surface mass balance is negative, so in those regions, but it's going to thicken where the surface mass balance has some snowfall. So it's kind of, it's a response that is expected, and you also see the other thing I want to point out is that, well, if you squeeze maybe here, it becomes red is thinning. It thins a lot towards the margins, and it doesn't thin as much towards the interior. If I now look at how much each basin loses mass, then this is what there is. As a reference, a 1 centimeter of sea level rise is this dot. So you can see that now, if I try to understand the sensitivity of my ice sheet to atmospheric forcing, the basin that the most dominant is North Basin, followed by all of the western coast. In the eastern coast, basically, the increase in mass due to the increase in snowfall, basically, is wiped out by the melting area, so you have basically not very much change. If I now look at the patterns of the sensitivity of my ice sheets when I'm doing an experiment, when I enhance the flow underneath the ice by I'm asking them to double their sliding velocities, I get this type of response, which is really different, again, than from the previous one. The key point I want to show you is that, first of all, my whole of my ice sheet is affected and it's kind of lowers down. You also have basically strong thinning in the interior of the catchment basin, but the increased slidiness meant that a lot of the ice was advected towards the edge, so you actually have growth along my margins. It's very particularly still, you can see it very well in 79 North, basically my ice grows. Okay. My dominant basin is this one. The southeast is the south is losing a lot of mass, about 2 centimeters of sea level equivalent, and then all of the western coast is again very sensitive. I want to come now to my come back to my two patterns. My point here is to convince you that the ice sheet responds very differently to my different forcing, and that's really nice because if I combine them, if I just add them, if I add this, the atmospheric response to the sliding response, I get this very complex signal where basically whenever you have a mass, whenever the ice thins in one experiment but grows in the other experiment, then basically they kind of cancel out. Now, you can also understand my complex pattern, which is this one here, towards Peterman's Glacier. I have a strong thinning towards the periphery of the ice sheet, but that's not caused because it's not due to my enhanced basal sliding, it's due to my warmer atmospheric conditions. And that's, for me, the power of the linearity of a signal, is that you can really kind of go back and identify the source of your change. So now I need to convince you that this response is the same as the response that I would have had if I had put my two forcings at the same time. So if I was doing a simulation with both the atmospheric forcings and a simulation with both the enhanced sliding forcing. Well, here it is. It's fairly good. You can see, again, you can really guess where the ice sheet is no longer susceptible to, for example, the thinning. The limits are kind of match really well. So but the key point to take here is that this complex signal, which is nearly the same, which is the same in those two parts of the diagram, is coming from two very distinct responses. It's not a one-on-one, really, linearity, because otherwise my sea level loss would be the same. And actually it's not. So there's not a total linearity, but it's a very good way for you, if you have a complex signal in thickness change, to try to understand the source of your response. So I wanted to kind of continue this. I was showing you the ensemble mean. And I wanted to convince you that what I was showing you was not a result of me averaging 8 models. If I'm taking 2 different models, the same story applies. You have a very characteristic response to the atmospheric forcing for 2 models that have 2 different physics. You have a distinct response for the sliding. If you add them together, then you get, the story is the same. This fingerprinting story is the same. So what is the implication? For me, the implication is quite strong. The fact that, for example, if you look at the atmospheric response for those 2 models is the same. If we had plotted some volume curves, they would be the same too, but they have different physics. The reasons they are the same for those 2 models is because they apply the same surface mass balance. The spread in the curves that we had for the other other models for the other climates, if I look at my fingerprint analysis, the reason that they do have this spread is because the surface mass balance that they apply is slightly different. The major big difference, and this is where I will stop. So basically, if you, just 2 more points. If you can quantify quite well your future atmospheric forcing, you will be able to reduce uncertainty in your sea level rise from the atmospheric. However, we do have a big problem for every time we try to understand the sensitivity to a dynamic forcing that involves flow at the bed, which is really illustrated here, that we really don't know what the basal slipperiness is beneath the ice sheets. And those 2 models respond very differently for that reason. They have a different sliding initially. So if you don't believe me, you'll have to look at the Searise paper, but that's really the crux of the story. So there are some limitations that we will always be faced as ice sheet models due to the fact that we don't know, for example, the basal boundaries. Thank you.
And we have 43 seconds for a quick question, if there's any.
Yeah, I know. Okay, so
okay.
And in case you didn't believe me about the meltings, it's the same thing for Antarctica.
Any 33 seconds in a question? No, okay. Let's move along. And last talk is by Anders. You want to do the keyboard dance?
I don't care. You pass
yeah,
me.
you need to.
Sure.
Thanks. Okay.
So good evening. If I'm not giving a talk at all, then we are in time, right? So I'm trying to be short. I'm obviously not Ricarda Winkelmann, and I'm sorry that she can't be here. I'm trying my best to give the talk properly. This is actually about a mechanism and then a quantification of a mechanism, and that is that we say that there's increased future ice discharge from Antarctica owing to snowfall. That doesn't mean that we'll have a net mass loss, but there will be increased ice discharge. And let's try to understand how this can come along. This is the mechanism. I'll show this right in the beginning, and then we'll discuss the quantification. If you have snowfall on Antarctica, then it'll elevate the ice elevation differently depending on whether it's falling on grounded or on floating ice. That is very, very simple, and you all know this. So if you have this is now a strange picture where you have more snowfall on the shelf, but if you just assume that there's the same snowfall on grounded ice and on the shelf here, then because of the floating, most of the additional elevation will be compensated by sinking in of the ice on the floated part. And this will change the driving stress at the grounding line, and this is what you see here. This is the additional driving stress if you have an experiment with warming of the ice only and one where you have additional snowfall. So this is the whole mechanism. It's very simple, and it was actually mentioned before in the famous 1999 paper by Philipp Heubrechts and de Volt, but they quantified it to be rather small, of the order of 10%, and the only thing here is that we think it's a bit higher. So let's put this in perspective. If you want to compare the effect of the snowfall with the effect of basal ice shelf melt, which is very often considered to be the most important driver of ice changes in the future in Antarctica, then they actually have already the same unit, which is meters per second or meters per year. There's no meters per second in glaciology. I learned this. There's meters per year. Okay. So if you compare this, these two numbers, then if you are interested in the effect on the driving stress, then the basal melt has to be 9 times as high as the precipitation in order to get the same effect with respect to the driving stress. Now, the basal melt is doing something else. It is changing the buttressing, and this effect is not considered here. But if you just compare this, the effect on the driving strength, then it's quite clear that it has to be 9 times bigger, the basal melt, than the precipitation. Now, this is not the case in most places of Antarctica if you take these numbers here. So let's see now. We want to quantify the effect using a rather coarse resolution climate model, ice model. You've heard about this PISM PIC, the parallel ice sheet model from Potsdam. Before, you've heard about the parallel ice sheet model that was is developed in Alaska, and we just for a short period took the model, put some additional things in there, and now we merged it again with the people from Alaska at Bühler and colleagues. What we have is, I think this is the same in GRISLI, we have a representation of the transition zone by simply superimposing the SSIA and the SSA approximations, and what we have additionally, well, this is what you get then for the velocity field. You span quite a range of velocities. These are the observed fields, and this is the modeled field. It's plotted in log, so it's not surprising that we're not so far off. But what I want to show you here is that we span at least 3 orders of magnitude as the observed values too. We have a subgrid ice front parameterization. This is not important, but it's the difference to the PISM model, and we have a carving law, which is all now in the PISM model too. Now, this is how Antarctica looks then if you let PISM PIC run into equilibrium with present-day boundary conditions, and you see that we get the streams, in a rather coarse fashion. If you zoom in there, you probably find a lot of discrepancies compared to observations. However, we get some streams, we get them, and when you look at the continental scale at the right places. Now we want to do scenario simulations. That was actually thought to enter the IPCC, but what I actually did eventually was using the Searise experiments, using the 5 ice models, and combine them with climate simulations and the linear response function theory in order to give projections for the IPCC. But the projections we did with PISM were not completely in vain. We used them for this study here. So what we put was we put some surface temperature increase that we downscaled from global mean temperature changes, which was shown by Katja Frieler that this is actually quite good, that quite easily done. The basal melt also was downscaled from the GCM simulations of the CMIP5, but they were combined with the box model by Helmer and Olbers and Helmer in order to get the temperature increase at the base of and the basal melt then. And we had some precipitation changes where we used the parameterization by Heubrechts and de Volt that I mentioned earlier. What we did actually was we didn't just produce one parameter configuration of our model, but we put 81 of them, and this is the model spread for the outcome that you get for the different RCP scenarios, the representative concentration pathways. The red one is the RCP 8.5, which is really burning hell. In some models you get 15 degrees of warming in 2200, it is really, really a very strong scenario. Now, I'm not convinced with respect to the net sea level rise that you get from these simulations, but what is the point here is we actually get no net loss of ice, as you see here in these simulations. And we think we can do better now. But the point here really is the relation between the additional ice that you put onto Antarctica, which is the cumulative snowfall, and the ice loss that you get through additional ice discharge just from this effect of additional precipitation, right? So we did all these combinations of surface warming plus precipitation, only surface warming, basal melt plus precipitation, all these combinations. And from this you can extract the contribution of ice discharge that you get only from the precipitation effect. And this is about 30% up to 65% of the additional ice the additional ice that you produce by cumulative snowfall. And this is a significant effect. It is much higher than the 10% estimated previously, which we think is due to a different representation of the transition zone. This can obviously change if the transition zone representation changes, and the further studies are necessary in order to really quantify this even further. But here we get this result of 30 to 65%. Thanks, that's it.
We do have time for a question, and before you guys leave, I want to make some points, but do we have any question? Everybody's very approved at the end of the day. Thanks, Anderson. So before I put you back on to the light, 3 small announcements. First, thanks to Bob and Chandra and Anders to helping organizing or co-organizing this session. Sorry. Second point, this session I requested was taped and video on demand, so I think that's what we're helping us. And thanks. You can go on the web and see back the presentations and listen to them. So this is a good use of technology. Thanks, AGU. And third, posters tomorrow afternoon. I know it's a tough call, but one thing that I really do need your help is for the OSPA judges. If you're around tomorrow afternoon, stop by the poster session area while you're going, to the Golden Gate Bridge or going for a stride, because we do really need all the students evaluated by 3 judges, and it's very hard to find somebody. You go to the AGU website, register as a judge, OSPA, you can pick up those who are still in needs. It will show you the list, and then you just go to the posters, you will find all the criteria evaluation, and then you can fill everything electronically by December the 10th. So don't get forms, it's not a big trouble. You sip a cup of coffee when you go back home and you fill your grades in so that the students can be evaluated. So please do so, so that they get a chance to get an award if they deserve it, and they need all our support to do that. So thank you very much to everybody, and enjoy your Thursday night.